Hello everyone and welcome to our calculus notes for section 6.1. Today we're going to be talking about the area of a region between two curves. And we want to learn how to express this as a definite integral. So what I have here are two curves, f and g, and we'll just take a look at the f curve right here. And if we want to find the area under the curve between a and b, that we can see right in here, we know we can find this area by finding the definite integral from a to b of our function f of x with respect to x. Okay, and that will give us this area right in here. Now if we look over here at our next function and we look at our g function, and we want to find the area from a to b. Now we're looking for the area right in here, and we know this area is given by the definite integral from a to b of g of x with respect to x. And so that is this area right here. Now I'll just label this area sub 2, and we'll label the other one area sub 1. And what we want to try to do now is be able to find the area between these two curves. Okay, so right in here. Well, geometrically, if we're looking for this, we'll just call it a sub 3. Hopefully you can see that a sub 3 would just be taking a sub 1 and subtracting a sub 2. Okay, so if we take all this area and then we subtract this area, we're going to be left with a sub 3 right here. So if we want to write this as an integral, a sub 3 would equal, well, a sub 1, which was the integral from a to b of f of x dx, minus a sub 2, which is the definite integral from a to b of g of x dx. Okay, so this is how we would find that area a sub 3. Now we can also think about this using our representative rectangles. Okay, and it's going to apply the same thought process that we did before when we were dealing with just finding the area under one curve. So if I were to take this and divide it up into rectangles, okay, much like what we were doing before, we know the area of a rectangle is base times height. Now in this case, what is our base? The base is going to be our delta x, just like it was before. And how would I find the height? Well, if we take a look at this and we trace this over to the y-axis, I would call this f of x sub I. And then if I trace this point over to the y-axis, I would call this g of x sub I. So basically it's the function evaluated at the point. And so if I'm looking at the height here, it's going to be the difference between f of x sub I and g of x sub I. So we have f of x sub I minus g of x sub I. So if I were to find this area by plugging in for my base and my height, I would get the height is f of x sub I minus g of x sub I times delta x. Okay, and we know then that we're going to be taking an infinite amount of rectangles here and letting my delta x go to 0. And so we know that this is the same thing as taking the definite integral. So here we have the definite integral from a to b of f of x minus g of x with respect to x. Okay, now we could have also seen that if we take our definite integrals here with the same limits of integration, we basically would just have to combine these into one right here. So all in all, to find the area of a region between two curves, all you have to do is take the definite integral from a to b of f of x minus g of x with respect to x. Now, this is given that f of x is greater than g of x on that entire interval. So you can see our subtraction process is only going to work if we put the taller function first. So let's give some of these a try. Okay, so we want to find the area of the region between the two curves, x squared plus 2, which is right here, negative x, which is right here, on the interval 0 to 1. So from 0 to 1. So the area we're looking for is right in here. So we'll just label these here. Here's your f of x, and here's your g of x. And if we want to find this area, all we need to do is take the definite integral from 0 to 1 of f of x, which is x squared plus 2, minus g of x, which is negative x, with respect to x. And you'll notice that I do put the functions here in parentheses. Just when you're subtracting, we have to make sure that we distribute that negative to the entire function there. And so now we can simplify this. So the area will equal the definite integral from 0 to 1 of x squared plus x plus 2 dx. And so notice all I did here was change my signs and then rewrite this. Now at this point we can solve because we know how to take a definite integral. So the definite integral of x squared plus x plus 2 is going to be x cubed over 3 plus x squared over 2 plus 2x, and we're going to evaluate that from 0 to 1. So we're going to plug in our 1 first. 1 cubed over 3 plus 1 squared over 2 plus 2 times 1. And this is going to be minus 0 cubed over 3 plus 0 squared over 2 plus 2 times 0. So we're left with 1/3 plus 1/2 plus 2 minus 0. And if we turn these all into sixths, we end up with 2/6 plus 3/6 plus 12/6 for a grand total of 17/6 for the area between the two curves. I want you to try the next one on your own. Go ahead and pause the video and then come on back when you're done to check your work. Alright, welcome back everybody. So you should have blocked off this area right in here and set up your definite integral by taking the upper function minus the lower function, and then that reduces right there. And one note is that you can use your calculator to find these definite integrals. So just use FNINT or whichever method you prefer, but you should have come up with an area of 50/3. Alright, next we want to talk about the area of a region between two intersecting curves. Okay, so you'll notice in all the previous examples we were going between two regions, and that would be given to you in the problem right here. Now what we're going to do is just say find the area of the region between the two curves. So we're going to take a look at two different types of functions, functions of x as well as functions of y. So if we're looking at finding this area right in here, okay, we can see that they intersect at 2 points. And I'm going to call this the left intersection, and this is the right intersection. So when we go about finding our indefinite integral, that's the left and the right that we're talking about here. And notice it's going to correspond with the x values at that point. So it's the x value of the left intersection and the x value of the right intersection. Okay, and again, this is all because we have functions of x. Now, the next part is kind of what we were doing before. It's going to be the top function minus the bottom function. So here, this one would be considered our top function, and then this one would be considered the bottom function. Okay, so all you have to do differently from what we were doing is identify the x values of the two intersections on the left and the right, and then take your definite integral. And you'll notice here, if we were trying to draw rectangles, representative rectangles, they would also be vertical. Okay, so let's go ahead and try some examples here. Okay, so it says find the area of the region between the two intersecting curves, and so we can see they intersect right here, and then the shaded area that we're looking for would be right in here. Side is this horizontal or vertical rectangles as we go through this. We have to be able to make rectangles across this entire section here. So looking at this, these are actually going to be vertical rectangles. As you can see, I could make them all the way across anywhere on that interval. And let's go ahead and identify our f of x and g of x. So here's our f of x function, and here is our g of x function. And the next thing we have to do is find the intersections. To do that, we set f of x equal to g of x, and then solve. So we're going to say 2 minus x squared equals x. And then this is just a quadratic function that we want to solve, so we're going to set it equal to 0. And I'll put this in order here. And it's probably easiest if x squared is positive, so I'll change all of the signs. And then I can solve this by factoring. So we get x plus 2 times x minus 1. And so I have two solutions for x. X equals negative 2 and x equals positive 1. Okay, and you can see those right here. So here is the x sub L, or the x on the left endpoint. And then here is the x on the right endpoint. And you can see that is where they intersect. Okay, so now we want to follow this pattern right here. So it's the integral from the left x to the right x of top minus bottom dx. So the area is going to be the integral from negative 2 to 1 of my top function, which is going to be 2 minus x squared, minus the bottom function, which is just x, and with respect to x. And so if we simplify this, we have negative 2 to 1 of, well, negative x squared minus x plus 2 with respect to x. And if we just solve this using our calculator, we're going to get 9 halves. All right, in our next example, we want to find the area of the region between the two intersecting curves. So we have 3x cubed minus x squared minus 10x, and that's given by this curve right here. All right, and then g of x is 2x minus x squared, and that's given by this curve right here. So now when these two curves intersect, we actually have two different regions formed by the intersection. So one of them is over here, and then the other one is over here. Okay, now in the first intersection, we're going to see that there's a different function on top. And so in this one, f of x is actually on top, and g of x is on the bottom. Okay, whereas in the second intersection, now we have g of x being on top and f of x being on bottom. So to actually find these areas, we are going to find the areas separately and then add them together. Okay, so first off, we do need to find our intersection points. All right, and to do that, we're going to actually set the functions equal to each other. So 3x cubed minus x squared minus 10x. And we're going to set this equal to 2x minus x squared. Okay, in order to solve this, we want to get it equal to 0. So we're going to subtract 2x and add x squared. And that will give me 0 here on the right-hand side. So we're going to subtract 2x, and I'll line it up with like terms here, and add the x squared. All right, so we're left with 3x cubed, and then minus 12x. The x squared terms cancel out there. All right, now to solve this, we do want to factor, so we can factor out of 3x, and we're going to be left with x squared minus 4. And this is a difference of two squares, the x squared minus 4. So we get 3x times x plus 2 and x minus 2 equals 0. And our solutions here are x equals 0, x equals negative 2, and x equals 2. Now what that gives us is all of these intersections. So this one is happening at x equals negative 2, and you can kind of see that there in the graph. This intersection happens when x equals 0, and then this intersection is happening here when x equals 2. All right, so in order to find the first area here, that is going to be our definite integral, and we're going to go from negative 2 up to 0. Now the top function in this case was f of x, okay, so that's going to be the 3x cubed minus x squared minus 10x. And we're going to subtract the bottom function, which was g of x. Okay, so in this case, g of x is 2x minus x squared. Okay, and all of this is going to be with the variable of integration, dx. So we can just figure out what this is going to be, and that's going to be the area of the first region. And then we're going to want to add this. We're going to want to add this to the area of the second region. And so that one's going to go from 0 to 2. Okay, and then the upper function now switches. So the upper function here is the g of x function. Okay, and that one is the 2x minus x squared. And then minus the bottom function, well in this case it's f of x, which is 3x cubed minus x squared minus 10x. And that's also with respect to x. So we can actually use Desmos to calculate this definite integral for us. If you hit functions and go to miscellaneous, then you get to the definite integral. So our first one is going to be negative 2, and it's going to go to 0. And then we can type in the definite integral we came up with. So that'll be 3x cubed minus x squared minus 10x, and then minus, and then our second function we're going to put in parentheses here, so that's going to be 2x minus x squared. And then dx, we have to go to the keyboard, and we can see that that first function was 12. Now the second one, we'll do it again. So functions, miscellaneous, definite integral. Now we want to go from 0 on up to 2. Okay, we start a parentheses for the whole integrand, and now we get the 2x minus x squared. Okay, and then minus the bottom function, and that is the 3x cubed minus x squared minus 10x. And we'll do with the respect to x. That is also 12. So when you add the two together, you should get 24. All right, for our next example, we're going to use Desmos Only here and see how that goes. So let's go and type in our functions to Desmos. So we have f of x, and that's going to equal, here in the functions, sine of x. And then we have g of x, and that's going to equal, in our functions, cosine of x. All right, now the way this works, you're going to have lots of space that's intersecting, and it turns out that each one of those has the same area. So we're going to focus in and just find the area in between these two right here. So I'm going to show you how you can actually find the intersections. So in Desmos, if you just tap on the intersection of two functions, it will tell you the points there. So we know that this is going from pi over 4 to 5 pi over 4. So extremely helpful. We don't have to set sine of x equal to cosine of x anymore. We can just tap on the two there and get our limits of integration. All right. So if we want to find the area between the two curves, we want a definite integral. And what were those again? I'll just tap on them. So it's going to go from pi over 4. So pi over 4. And then 2, well, this one's at 5 pi over 4 right here. So 5 pi over 4. That works great. All right, now we have our integrand. Now there's another time-saving tip here. These functions aren't particularly long, but we've already typed them out and we've named them. So we have f of x equals the sine of x. And it looks like that's on top here. So what we can do is we can just put our f of x function right here. And we're going to subtract the bottom function, which is cosine of x. And so we can actually just put g of x right here. And that's going to subtract those two functions. And then we can go with respect to x, and we get our answer, 2.828. So, you know, these are pretty easy to type in, sine and cosine, but if you have longer functions and you've already named them with f and g, then you can just use those right there. All right, and in our final example, we're also going to just use Desmos here. So we're going to type in our functions here, and our first one is y is equal to x plus 6. Now, in the last example, we had the benefit of labeling it as f of x. So if we write y equals x plus 6, and we write our next one is y equals x cubed, like that, and then this one actually has 3 functions, so y equals negative 1/2 x right there. Oops, we'll come out here. X right there. We can take a look at the area between the two, actually 3 curves now. So what we can do, when everything is just y equals, Desmos doesn't really differentiate between them. So what we can do is when you're typing this and you type y, you could actually put a 1 after that, and that is now labeled as y sub 1. So you can do that for all of them, y sub 2 and y sub 3. So now we can use these equations using the names y1, y2, and y3. Now, I actually want to shade this region because as you look, the top function is always this one right here in green, the x plus 6. On the first little interval, the black function, or negative 1/2 x, is on the bottom. And then for the second little part, then negative 1/2, then x cubed, the purple function, is on the bottom. And so this is actually going to end up being two separate integrals. And I want to show you how we can shade this. So what you do is just pick the bottom function, and that's going to be y3. And we want to make that less than or equal to y. So we're actually making a new function with inequalities, and that's going to be less than or equal to now the top function, so the one in green, which is y1. And you can see there's way too much there, so we do actually need to limit this domain. And to do that, you have to go into your keyboard and use the curly braces. And now we do an inequality with our x's. So if you tap on the point, it's negative 4, 2. So this really starts at negative 4, and then is less than or equal to x. And then that's going to be less than or equal to, well, our next intersection point happens at 0, 0. So we can just put a 0 in right there. And that's the first little area we have to find. The second area, notice that the green function is still on top, but now the purple is on the bottom. So always start with the bottom function here. So this is going to be y sub 2 is less than or equal to y is less than or equal to the green function, which is y sub 1. Now you can see we have way too much there, so we do want to restrict the domain with the curly braces. And this is going to start at 0, less than or equal to x, and then it's going to end, well, it already ended for us, but that does happen at x equals 2. And that's going to be important to know for our definite integral later. So there we go. That is our shaded region and the area we are trying to find. So let's go ahead and do this. Our first integral will be the one in red there, the shaded part. And this is going to go from, well, as we found out before, was negative 4. And it's going to go all the way to 0. And now here we can also use our defined equations, y1, y2, and y3. So the top one here is the green one. So we're going to put y1 first, and then we're going to subtract the bottom one, which was the black function, which is y3. So we'll do y1 minus y3, close the parentheses, and then put that with respect to x, the dx. Okay, so that red area there is 12. And let's go ahead and just add it since we have to. We're going to add the blue area here. And so we need another definite integral. And this one is going to start at 0 and end at, like we found earlier, 2. Now the top function is still the y1, so we'll do that. And then we're going to subtract. Well, now we want to subtract y2 from it. That's the purple function. And we're going to put that with respect to x. And we get a total of 22. So the red was 12, looks like the blue is 10, and the total area there is 22. So as you're showing your work, I definitely want to see a sketch with the shaded area. And then I also want to see this integral, the definite integral written out here like it is in line 6, and then your final answer. All right, so that's how you can use Desmos to shade these curves and also find the area between all these intersecting curves.